Myself, Dr. Dityaranjan Patnaik, and I am working as assistant professor in the Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management, Greater Noida. Today we will see the numerical problems related to ASK, FSK and PSK. Before that, we have seen about the basics of ASK, FSK, PSK, DPSK and QPSK. Now we will see some problems, numerical problems related to this basic modulation schemes. So we can write, we can see the problem number 1. A binary data is transmitted using ASK, this is the point, this is ASK over a AWGN channel, that is additive white Gaussian noise channel. This is the basic wireless channel. This is nothing but and these symbols are transmitted, this data, binary data are transmitted at a rate of 2.4 Mbps. Okay. Now the carrier amplitude at the receiver is 1 millivolt. This is the carrier amplitude. The noise power spectral density N naught divided 2 equal to 10 to the minus 15 10 to the minus 15 W per watts per hertz. Okay. So find the average probability of error if the detection is coherent and if the detection is non-coherent. So and hint is also it is given, take the ERFC of 5 equal to something value 3 multiplied by 10 to the minus 6. So here the modulation scheme is nothing but your ASK. So in ASK we are using coherent and non-coherent. Coherent means if I am using the local oscillator to transmit to receive the signal, and if I am not using this, and this is nothing but your non-coherent types of demodulation scheme. So here I have summarized the given quantities. So this is your RB. RB is nothing but your bit rate. Bit rate is nothing but your 2.4 Mbps. So from bit rate I can write the symbol, I mean time period of bit. So time period of bit is nothing but TB equal to 1 by RB. This is nothing but the 1 divided by 2.4 multiplied by 10 to the 10 to the 6. Okay. So as Mbps, that's why you said this is 10 to the 6. Similarly, for AC, that is carrier of the amplitude of the carrier signal is your 1 MB, and this is the your carrier of the amplitude. Similarly, this is the noise, that is your PST of the noise, that is power spectral density, noise power is nothing but your N naught divided by 2 equal to 10 to the minus 15 watts per hertz, from where I can get only N naught. What is this is nothing but the 2 times 10 to the minus 15 watts per hertz, and I have also given this ERFC of 5 is error function, complementary error function is nothing but the of 5 is nothing but the 3 into 10 to the power minus 6. So from this data I can find out the power. Power equal to nothing but the AC square divided by 2, that is amplitude square divided by 2. So AC I have given 1 into 10 to the minus 3, that square by 2, this is your 0.5 into 10 to the minus 6 watts, or 10 to the minus 6 nothing but the 0.5 microwatt. Okay. So but I know that EB, that energy bit energy is nothing but the power into TB, as same, that is power equal to nothing but EB by TB. Similarly from this expression, EB is nothing but equal to P times TB. So power I have calculated, this is the power, and times TB. TB is nothing but your 1 by RB. This is the TB. Okay, this is the 1 by RB. This is nothing but the energy. Energy, this unit will be joules. Okay, so your power, this energy would be watt. You should mark this. Okay, so for coherent ASK, I need, the question is your find the average probability of error. Okay, I want to calculate the probability of error. Okay, so for probability of error, I have calculated in the previous lecture. We have calculated half times ERFC of half multiplied by root EB by n naught. This is the formula. Okay, or if I will take this inside, then it would be root EB by 4 times n naught. Okay, so why I have calculated this EB? Because I need here EB. How much EB is EB is there for calculating the PE, probability of error. That's why I have calculated this much. EB equal to P times TB. So I know TB, but I don't know P. So for P, I have calculated like this. So just put the values for EB. I have 0.208 into 10 to the power minus 13. Okay, and for n naught, I have a, for n naught I have how much? 2 times 10 to the minus 15. Okay, 2 times 10 to the minus 15. Okay, that's why I will get half times ERFC of 5.10, ERFC of 5.103. So is nearly equal to, I will calculate ERFC of 5. Okay, so ERFC of 5 is nothing but in the question it is given as 3 into 10 to the power minus 6. Now it would be probability of error is nothing but your 1.5 into 10 to the power minus 6 when I am using coherent detection, coherent ASK. Similarly, for non-coherent ASK, it would be half times exponential of root minus EB by 4 n naught. Okay, so we have not calculated for non-coherent case, but we can calculate by using this formula. Okay, so half times exponential of minus, this is your EB and this is your 4 times n naught, and half times exponential of minus 26.04125. This is nothing but the half times this much, and I will get, this is the probability of error in case of non-coherent ASK. We can see that in case of coherent ASK, I am getting this much of error, but in case of non-coherent case, I am getting this much of error, which is better than the other one. Similarly, second example is based on FSK. Okay, so the question is coherent orthogonal binary FSK modulation is used to transmit two equiprobable symbol waveforms. Okay, two equiprobable symbol waveforms, that is S1t of t equal to alpha times cos 2 pi f1t. Similarly, S2 of t equal to alpha times cos 2 pi f2t. See, you can see that f1, f2 means both frequencies are different. That's why this is also known as FSK scheme. Okay, where alpha equal to 4 MB. Okay, this is nothing but your amplitude. Okay, assume an AWGN channel with two-sided noise power spectral density, that is your n0 by 2 equal to 0.5 into 10 to minus 12 watts per hertz, using an optimal receiver, and the relation here, this is the relation Q function relation. The bit error probability for a data rate of 500 kbps, data rate is also given, is how much. So we can see that in FSK, transmission of 1 is represented as S1 of t equal to AC cos 2 pi FH, that is higher frequency t. Similarly, transmission of 0 is represented as low frequency. Here this for 1, this is high frequency, for 0 this is low frequency. Okay, so bit error probability is nothing but your, in terms of error function, I can also write, and in terms of Q function also. Actually, Q function is also used to calculate the error probability of error. So the bit error rate is nothing but your, for FSK, Q of root ED divided by 2 n naught. So what is ED? ED is nothing but your energy. Okay, it is the energy of S1t minus S2 of T. So ED is nothing but how I can calculate the energy. It is nothing but the 0 to TB S1T minus S2T whole square dt. So I can get A minus B whole square, that is A square plus B square minus 2 times A into B. Okay, this is multiply 2 times A into B. Okay. So in the question we have given S1T and S2T both are orthogonal. Okay, both are orthogonal. That's why we can write like this: S1T minus S2T dt equal to 0. So ED only first two terms are existed. Okay. So S1 square of T, that is nothing but the S square TB by 2. Similarly S2 of T is nothing but your AC root 2 TB by 2, that is another S square TB divided by 2. After adding this, I can get ED equal to AC times AC cube times TB. Okay. So sorry, this is nothing but your ED this is nothing but your AC square times TB. Okay, this is S square 2 times plus 2 divided 2. This is S square AC square TB. Okay, so now I can find out the beta rate, that is Q of root ED divided 2 N naught. Okay, ED is nothing but your S square TB divided by 2 N naught. Okay, 2 N naught. So I have given that is alpha equal to 4 MB, that is nothing but carrier amplitude. Similarly, N naught by 2 is also given this much. So from this N naught I can get 10 to the minus 12. Okay, watts per hertz. Similarly, TB is nothing but your 1 by RB. We have given RB is nothing but your 500 RB, I think. Okay, we can say that if RB is given 800 times, so I can write this is the TB is nothing but 0.2 into 10 to the power minus 5 minus, sorry, this is I think 500 kbps. I can get the 10 to the 0.2 into 10 to the minus 5. Okay, so TB equal to 2, I can write 2 times 10 to the minus 6 second. So now I can write B equal to Q times Q of AC square TB by 2 N naught. So AC square, your AC is nothing but the 4 into 10 to the minus 3, that is millivolt, the square multiplied by TB. TB is nothing but your 2 times 10 to the minus 6 and divided 2 times N naught. 2 times your N naught is your 10 to the minus 12. Okay. Now I can get BAR as this much, and this is your BAR equal to Q times root over 16. Okay. Similarly, this is the again another problem regarding FSK. So a binary FSK system transmits data at a rate of 2 Mbps over an AWGN channel. So the noise power spectral density is this much. Determine the probability of error for coherent detection of FSK. Assume amplitude of the received signal is 1 microvolt. So here RB is given, okay, RB is given 2 Mbps and N naught by 2 is nothing but this much. So from here I can get N naught equal to 2 times 10 to the minus 20. So AC is given 1 microvolt, that is 10 to the minus 6 volt. So from RB I can get TB equal to 1 by RB, that is 1 by 2 times 2 times 10 to the 6, that is Mbps, that is 10 to the 6. So from where I can get EB equal to P times TB. Okay. So now I can get P. What is P? I know TB, but I don't know P. That's a P equal to S square by 2. So S square by 2 equal equal to 5 into 10 to minus 13 watts. Okay. So now EB equal to, this is P times TB, P is this much, okay, TB is this much. So P and this is TB, this is, it is nothing but this much of joules. So probability of error for FSK system is nothing but your P probability of error equal to half times ERFC of root EB divided by 2 N naught. So after substituting this value EB and 2 times N naught, I can get the ERFC of this much 2 times 2.2819. So I can get half times this is the ERFC equal to 1 times 1 minus error function of something. Okay, this is the we have already seen in the probability chapter. So this is the relation between ERFC and ERF. Okay, this is ERFC. So I can write ERF of this much equal to 1 minus ERFC equal to 1 minus ERF of 2.2819. So half times 1 minus is this is the relation. Okay, again. So from table error function table, I can get ERF of 2.2819 is 0.99959. So now at last I will get PE that the probability of error is 2.05 multiplied by 10 to the power minus 4. Now we will move to problem number 4, which is based on your PSK modulation scheme. So question is given as binary data is transmitted over an AWGN channel using BPSK at a rate of 1 Mbps. It is desired to have average probability of error, that is PE is less than equal to 10 to the minus 4. So here the question is something like different. Already given that PE less than equal to 10 to the minus 4, noise PST is given. Determine the average carried power required at receiver input if the detector is coherent type. Okay, and this is given. So RB is nothing but 1 Mbps, from where I can get TB equal to this much. N naught by 2 is given, from where I can get N naught. So here condition is given that P is less than equal to 10 to minus 4 and ERFC of 3.5 equal to 0.00025. Okay. So for BPSK, that is, this is BPSK, this probability of error is nothing but half times ERFC of EB by N naught. So already given that at most I will get 10 to the power minus 4 of probability of error. So here probability of error is given half times ERFC of root EB by N naught. Okay. So before 3 examples, we are calculating EB. Now P is given. I need what is EB. Okay. So ERFC of EB divided by N naught equal to 2 times 10 to the power minus 4. So ERF of U. Okay. ERF of U is nothing but 1 minus ERFC of U. So ERF of U equal to 1 minus how much it would be? That is ERF of root EB by N naught equal to 1 minus ERFC of root EB by N naught. Okay. So ERF EB by N naught, that is U, equal to 1 minus ERFC of root EB by N naught, that is ERFC of root by N naught to the 2 times 10 to the minus 4. This is nothing but this. So ERF of U equal to 0.998. I can get this U. What is the, for what value of U, that the error function would be 0.998. This would be nearly 2.8 or 2.9. From error table we can find out this. Okay. So for this now I got this is a 2.8 or 2.9. So for root EB by N naught, now that root EB by N naught equal to your 2 by 2.8. Okay, this is u. This is nothing but the u. Okay, so EB by N naught equal 2.8 square. EB by N naught equal to now 7.84. From where EB equal to N naught times 7.84, and I have given that N naught equal to 2 times 10 to the minus 12. Now this is the EB. Okay. So your EB PTB. So PTB equal to nothing but your this much. Okay. This is your EB. EB is nothing but your PTB. Okay. So this is the point where P equal to 1.568 minus 10 to minus 11 divided by TB. TB I have given this much. Okay. So I can get power equal to this much. Okay. This is the 1.568 10 to minus 5 watts. Similarly, this problem number 5, it is we can see that binary data are transmitted at a rate of 10 to 6 bits per second over a microwave link. Assuming channel noise is AWGN with 0 mean and power spectral density at the receiver input is 10 to minus 10 watts per hertz. Find the average carrier power required to maintain an average probability of error. Same type question for coherent binary PSK. This is binary PSK. Okay. Determine the minimum channel bandwidth required. Now the question is how much channel width is required to achieve this much of error. Okay. So RB is given, from where TB is calculated, same, and naught is also calculated, and I have given P equal to 10 to P less than equal to 10 to the minus 4. So for the PSK system, I know that probability of error is equal to this much. So probability of error is already given. So I will follow the previous one, and I got the U equal to 2.8. So from there EB by N naught equal to 2.8. Now I got this EB equal to this much. Same question, same type. Now EB equal to PTB. So P, I got this P is this much. But our bandwidth relation is bandwidth equal to 1 by TB. That is nothing but your rate. So BT equal to how much? Your, because TB equal to this much, that's why BT equal 1 megahertz. Okay. Similarly, compare the average power requirements of binary non-coherent DPSK, FSK, coherent ASK and PSK signal schemes operating at a data rate of 1000 bits per second over a band pass channel having a bandwidth of this much, and this is the noise power spectral density, this is the probability of error. Okay. So RB is given, TB is I got, BT, that is bandwidth is given, N naught by 2 is given, so I got N naught, so P is given. So probability of error for BPSK, that is this much. So probability of, after doing this, I got the EB equal to 9 times 4, 9 multiplied 4 times N naught. So P equal to half times ERFC of EB, 4 times N naught, the BFSK. So after that, probability of error equal to how much? Probability of 10 to minus 5. But 2 times this, that's why this is 2 times 10 to the minus 5. This, after doing this, I will get power equal to this much, and this is the relation, nothing but. So from error function I got U of 3. After getting the U of 3, I got this power is this much. Okay. So for coherent PSK, this is the error probability. Okay, this is the error probability. So this is nothing but the only difference is the how much this inside the ERFC function. Okay, so here I got the power as 1.8 in 10 to the minus 6 after performing the same steps. Okay, so for non-coherent FSK, this is the exponential function, and same, if I will follow this same procedure, I will get is the power as 0.938 times 10 to the minus 6 watts. Okay, so this is your error function table where I got this the values from that like ERF of something for which value of U I got the error function like this much. Okay, so I am calculating the year FC something, and from this table I am getting this. Okay, let's say for 0.64 to 03 year of U, I get U equal to 0.65. Like this, we have solved some problems. Now we can stop this session. So thank you very much. We'll see in the next class some new topics. Thank you.